Hello everyone. So again, welcome back to the latest lecture session. What have we been up to in the previous session anyway? So we have been looking at a particular case study, right? I think it was with respect to a site that was used for finishing or polishing wood and used for also preserving wood and so on. And we looked at that particular site, which was contaminated to a great extent by among other contaminants, dioxins, right? And I believe a few heavy metals too, right? In that context, we looked at the timeline of the relevant decisions, at least as taken in the US. Again, we needed some particular study, so where we had data, and this is something that I could find, right? Again, as we saw anyway, it took almost 2 decades from the time that the site was discovered or listed as requiring remediation to the completion of the relevant job, right? So in that context, we looked at a preliminary, or what did the relevant people look at? Preliminary remedial investigation or feasibility study. Based on that, they came up with different alternatives. Then after a few years and other, relevant decision making, let's say, right? People end up with a record of decision, again a term used in the US, let's say, right, where they finalize solidification and stabilization among the other options available. I believe they also looked at bioremediation, incineration, excavation of the relevant soil and up to 120 feet and so on and so forth, right. And then we moved on to data looking at, let's say, the laboratory studies or the batch scale studies, let's say, right. As in at this stage, solidification and stabilization was finalized to be the relevant remedial technique, right. And then obviously to decide the relevant matrix, let's say the mixture of either cement, fly ash or any other additives, or in this context I believe we also looked at, or the relevant people also looked at, let's say, some proprietary admixtures or binders, right. So to look at the relevant effectiveness and also obviously the cost and such, we looked at some data. So let's just start from there and take it from there. So here we looked at successful stabilization formulas. So again, we are not going to look at the technical aspect here. When it's deemed to be successful stabilization formula, we understand that the relevant and physical and chemical changes that we want to bring about, were successful, let's say, right. And again, successful stabilization, let's say, and we looked at cases A, B and C, let's say, right, and one around 39 dollars per 1 ton of raw soil to treat, cost of formula to treat 1 ton of raw soil. Here it's 62 and here it's 17, the lowest. As we saw, I believe this is the one that was selected, but again let's just have a quick recap. So untreated soil, right, I mean that's the reference here at 1 years, and the ratios at which that was added, let's say, obviously as you can see 1 is to 0.2 is to 0.1, and here they also added activated carbon, probably because let's say if you have any other organics or such, maybe not maybe typically activated carbon acts as a very good adsorbent, let's say, right, for hydrophobic compounds and so on. So this could be one reason for addition of activated carbon. We already looked at addition of Portland cement and fly ash, right, and then here they also looked at 2 proprietary items, but that was only in case B, right, and dilution factor excluding water here. So what does it mean? So for 1 ton of raw soil, they have to add 0.32 tons of the relevant binders now, right. That's a considerable amount, if I may say so. Again, with respect to part B, let's say, not part B, option B, same case, but here they did not look at these relevant aspects or the typical binders, let's say, right. They try to look at some proprietary materials. Obviously, if I am trying to look at proprietary materials, I need to either have a trade off with respect to cost effectiveness, or effectiveness with respect to the relevant immobility or degradation, right, like say binding to years and so on and so forth. We will look at some data later. So they looked at some particular proprietary items, and here though you still see that for 1 ton you still have to add 0.26 tons of the relevant binding materials, which obviously is relatively a high amount or volume, pardon me, or mass, and thus the cost obviously, as you would expect, is relatively higher, right. So that's something out there, and let's look at the option that was selected in a bit more detail. Again 1 which is the reference here, and 0.05 and almost the same amount of fly ash, cement and fly ash almost the same amount, and so on. But here, as you see, obviously they decrease the relevant fractions of what do we say, the fly ash, cement and activated carbon. Thus obviously the savings in the sense that, you know, for 1 ton you only need to add 0.1 ton of the relevant binders and admixtures here, right. So that is one particular aspect. So obviously here you know, looks like at least to meet the thresholds, let us say A, B, C options did well, and obviously because the cost was remarkably less for this particular formulation, and also the volume of the particular treated soil is not going to be greatly you know, remarkably great or high compared to the initial volume, as in here as you see, or at least the weight, and thus I am presuming the volume too, right. Here 1.32 after treatment, here 1.1 after treatment, right. So that is something to take into account obviously, because let us say you need to look at disposal or such too, right, and that is one aspect, let us say. So let us move on to looking at in detail this particular aspect. So 7 acres, and as we mentioned earlier 50,000 cubic yards, and option C where you know, they chose cement, fly ash and activated carbon. As we saw, cement and fly ash at almost the same what do we say fractions, let us say, and considerable fraction of powdered carbon, but obviously as you see here 90% of the relevant mixture, the total, the final matrix is made up of the waste itself, right. So that is something to keep in mind. It is 90% because typically, you know, that is a relatively high value, as we have seen even in the couple of examples we have looked at. Let us say I think 70% or 80% waste is what we have typically looked at and the final what do we say mixture now, but here we see it is around 90%. So let us move on to more data here. So some other treatability study results just for our particular understanding here. So let us look at what we have here. So obviously we have different parameters here. Different compounds, pentachlorophenol, dioxins, polyaromatic hydrocarbons, and then the physical properties, right. So here we have total, right, and then we have this I think synthetic, or you know, this is a kind of a leaching procedure test, you know, slightly different from the TCLP test, right. I think here it this SPLP test tries to mimic the conditions when this particular what do we say waste, let us say, or the solidified waste is exposed to acid rain, and that is the SPLP test. They looked at a slightly different test here, not just the TCLP, right, and I think that is what we have here. Obviously the units here, right, and untreated, this is the untreated site. So treated, one option with respect to the 39 ton where we had 1.32 after what do we say treatment of 1 ton. And here again where the 62 per ton site where they use the proprietary materials, I think it was around 1.26 after treatment, right. So let us, and the target was obviously as you see, you know, different values out here. So let us just look at this data, let us say after leaching, let us say, so 8,200 for untreated. So after treatment by this particular 39 per ton or 1.32 option, we have 120, or they ended up with 120, pardon me. And then what is it now, here it is 12. Here as in the case where they used or tried, or the trial was done with the proprietary material, you see that the relevant concentration after leaching is almost 10 times lesser than the one where they just use cement and fly ash, right. But obviously the cost is considerably higher, right, almost 80% higher, but the key is that, you know, both of them are lesser than the target. The target concentration was supposed to be 200 microgram per liter. So you see that even the one with 39 per ton or just the cement fly ash contraption, let us say, is good enough to suffice or meet the needs of these particular targets. And again, how were these targets arrived at? If you remember, let us say they looked at a 10 to the power of -4 lifetime cancer risk, and then looked at what are the different targets for different compounds, right. And here let us say pH, so it is untreated here. Obviously after treatment, as we witnessed or you know, we understand from our logical reasoning too, they are trying to beat this test here other than TCLP, they are trying to beat the SPLP test, right. So again here they are trying to rise the pH, and again that is why you see from pH initially of 7 or initial pH of 7, they now ended up with pH of around 11.8, right. So that is something to keep in mind. So again same case with dioxins, but here maybe relatively lesser level of removal probably. So 320 here, and then after treatment, let us say by just the cement and fly ash mixture 12 and 14, not a great deal of difference, and both the relevant options are less than 30, right. So, obviously here it's picogram per liter is the units here or the units, again obviously pH it's increasing here after treatment, that is something that we see here, right. Moving on to the polyaromatic hydrocarbons, right. So, we have it in microgram per liter, so 2.8 initially, and here I guess it is less than the method detection limit. So, they just mentioned that it is less than 2.8 and looks like the standard itself is 10. So, even in the untreated waste the PAH was not a concern, right. So, physical properties, obviously what are the two aspects we typically look at, the unconfined compressive strength to look at the structural integrity of this mixture, and the permeability, or let us say depending upon the vendor, hydraulic conductivity, let us say, right. So, again pounds per square inch, right. Typically we said at least 50 pounds per square inch was good enough, here they looked at 100, right. But looks like obviously both the mixtures are remarkably, what do we say, doing pretty well in this particular aspect, right. They are meeting the standards, right. And again permeability, so it has to be less than 10 power minus 6 centimeter per second, right. I guess this does not do a great job in that regard, right. This yes to some extent, right, but this is not of the relevant standard by a great degree though. Again, why do we want the permeability to be less? The reason is that let us say if you have this particular matrix, let us say surrounded by the relevant soil or such, let us say, and you have water coming down, let us say here they were looking at acid rain, let us say. So, let us just think of rain though, and if there is rain and let us say this it penetrated the soil cap and so on, if your permeability is less, it will flow around over and around this particular mixture rather than through the mixture, right. That is obviously one of the reasons why they look at trying to minimize the permeability though, right. So, again that is something to keep in mind. Let us look at some other data here. So, here solidification and stabilization specifications for remediation, let us say, right, after remediation, this is after remediation, right. So, this is after application of that particular kind of method that we talked about, where they looked at cement fly ash and activated carbon, but the ratios and the fractions were relatively lesser, right. So, let us look at the leaching properties, let us say. So, leaching properties, we are looking at arsenic, dibenzoanthracene, PCP, dioxins, and then again physical properties, let us say, and volume increase. As I mentioned earlier, obviously volume increase is something that is remarkably relevant, let us say. So, let us look at the different options here. This is the average of all the treated what do we say batches, I guess, right. So, maximum of any batch, right, and here let us say batch size is around 500 cubic yards. So, the maximum, so they test different batches and this was the maximum that they obtained, this is the average and results achieved, but we have a particular note here, average of all performance samples collected during remediation, right. Again this is the average though, but of all the performance samples related to performance they took multiple samples, and when they say results achieved it is the average of all those relevant samples, right. So, let us look at the leaching properties first, let us say. So, again average is somewhere out here 50 microgram per liter, maximum slightly higher though, right. Let us look at anomalies, let us say, right. Here let us say 10, 15, 44, 6.6, that seems to be an anomaly here obviously, 200 and 300 here, 10 picograms. So, this is an anomaly because it is in picogram here and the maximum is almost remarkably high, 45 microgram per liter, right. And let us look at the permeability. So, here finally though as you see the permeability is less than what they were trying to look for, at least the average anyway, it was less than 1 into 10 power minus 6 and maximum here is less than 1 into 10 power minus 5, right. So, that is something that to be considered because the permeability is remarkably high, almost a factor of 10 high, though they do say it is just less than 1. The issue is that let us say you have a mixture, let us say, and they are looking at different batches and getting these results, right. So, even if let us say a cluster of batches are having relatively higher permeability, let us say, what can happen now? You can have seepage of that particular rainwater or let us say the leachate through that particular batch, because at least though they say it is less than 10 power minus 5, we do not know if it is what do we say 10 power minus 5 or how close to 10 power minus 6 or such it is, there is a uncertainty factor almost of 10, right. So, this can be a critical aspect, can be anyway, right, but obviously if you are capping it and again using a relevant what do we say geosynthetic clay liner, that is going to limit or increase the effectiveness of the system, even though you have batches that have greater permeability, right? But that's something to keep in mind. Obviously, the average is again around 1.02 into 10 power minus 6, closer to their particular requirement of 10 power minus 6 into, 10 power minus 6 centimeters per second. So, the average of all the treated unconfined compressive strength results were greater than 100 psi, and again here it is 2 I guess, right. So, again volume increase was less than 30%. 35%. So, looks like different batches they observed different levels of increase in volume, but as we looked at it in our case, let us say in our case as in earlier, we saw that the fraction was for 1 ton they were adding I think 0.1 ton, right. Anyway, so a total of 1.1 let us say initially when we had only 1. So, around 10%, but obviously we are looking at we need to consider the density, but that is something to keep in mind here, right. So, again generally did well, but again something to keep in mind is that because of cost effectiveness, obviously you can obviously while you can obviously go much lower, because people look at what we say the feasibility, cost obviously plays a role and time plays a role too, right. So, keeping these two aspects in mind, obviously though we have standards, people look at the overall picture. It is not that we are going to be very picky, let us say, with respect to 1 or 2 variables. Obviously some of the relevant more what do we say variables, or those variables that have more weightage, let us say in terms of risk or the criticality, let us say, obviously we are going to look at that, but we are not going to be very picky with respect to all the relevant aspects too. But again, as you see here, there is a variation between the average and the maximum, and again that is something to keep in mind here, right. So, let us move on. So, let us look at for the final site, let us say major bid cost components for the remedial action, right. This is for the major bid. So, let us look at what are the aspects that are leading to the relevant or require resources in the first case. So, paperwork, mobilization and documents, right, that is something. So, first demolition and debris of the existing or clearing the debris of the existing structures if any, and there is already some NAPL present and that needs to be recovered, that is adding to the cost. So, a cutoff wall, and again when do we use this cutoff wall? Obviously now let us say here this is playing the role of the containment or the barrier now. If you remember in one of the earlier examples with respect to our solidification and not solidification, pardon me, remediation of the relevant sediments, we talked about different aspects and we talked about cutoff walls obviously being used in conjunction with other techniques. So, again what is the role here? It is just containment, let us say you do not want this particular contaminant to what do we say be transported over a wider distance now or area, pardon me. So, they have a cutoff wall here. So, drainage trenches again going in conjunction with cutoff walls, you want to drain out the relevant groundwater, let us say. So, here is the major aspect: excavate, treat and replace the soil, right. You are going to excavate it, treat it and replace it with either the treated what we say mixture or typically fresh soil or uncontaminated soil, and contaminated water treatment, right. The creosote, right, looks like it requires what is a specific disposal, and the cap again. So, after your particular what do we say solidification and stabilization, you are also going to, or these people also looked at, if you remember the record of decision, a cap, soil cap and then a geosynthetic clay liner, that is what you see. So, synthetic, what do we have here? Geosynthetic clay liner and 2 feet of soil, that is the cap here, and then once they are done with it, site restoration and demobilization and other petty aspects, right. So, the total seems to be, it was almost 3 million, right. Let us look at what are the major components in here, right. Obviously, as you would expect, excavation, treatment and replacing the soil is a major component, almost 2/3 of the relevant cost, right. Almost 2 million out of the 3 million, right, that is from excavation, treatment and so on. Other aspects obviously are the major aspects are the cap, right, and obviously NAPL recovery, let us say, right. So, these are the major aspects again as you would expect, the solidification, stabilization, the relevant excavation as we looked at earlier. I think we looked at one case for excavation of the Moradabad site and how much amount money it would cost. So, again excavation, treating and replacing the soil is major aspect here, but obviously there are other aspects that add up to considerable fraction too, right. But I believe if you look at the relevant initial estimates, this particular estimate either met that particular estimate or was lower than the relevant estimate for this particular site. This is from the major bid though, right, from the bid for this particular site. Again, let us move on. So, let us just look at the timeline again for our understanding, let us say. So, final remedy was selected in 1996, but keep in mind that they started what we say looking at the site from 1981, right. Obviously, what I am trying to impress upon the relevant people here is that remediation is a time consuming what do we say process now, right, either with respect to being able to, let us say, commit enough resources and also being able to come up to a worthwhile conclusion, not conclusion, let us say alternative part, right, to come up with a worthwhile alternative here, right. That is something that is very important, because let us say I come up with a wrong alternative, right, I am going to mess up the relevant situation and it is going to take more resources, more time to be able to what do we say remediate this particular site again, right. But what do people do? They take temporary measures so that this contaminant does not spread out during that particular time. It could include some of those extraction trenches, let us say, or cut-off walls and so on, or some cap in the meantime. I mean in the meantime, as in these 2 decades, as you see we started out at 1981 and it was completed in 2000 now, right. So, it is a long drawn process. Obviously, whenever possible we would like to have what we say look for prevention, and so that is something that at least we should strive for in the Indian context. I mean, we are only now moving from agricultural economy to an industrial economy. Obviously, there are going to be issues, right, people trying to make money, enforcement lagging behind and such. We are never going to have the ideal case scenario, but as you see, right, there are going to be legacy issues, as in even after the site is closed you are going to have what we say issues for decades and decades and decades, right. So, that is something to keep in mind. And regulatory status looked at, the treatment was for only a period of 2 years, I believe 98 to 2000 or 99 to 2000, right. So, that is something to keep in mind, but the decision making and the relevant process, let us say, and also the relevant studies, primarily the risk assessment and the preliminary remedial investigation and feasibility studies, they obviously take time, right. So, and then after that again EPA or the US EPA has a policy of 5-year review for all these contaminated sites. So, that is again something maybe we can imbibe. Again, we need to learn from some of the relevant aspects out there, let us say, or about how to do things or how not to do things too, right. So, again, soil remediation was conducted at the site, was protective. Looks like the 5-year review says that it was doing the job, as an we looked at 10⁻⁴ threshold, what do we say, lifetime cancer risk. It was able to meet that particular objective, right, which was for the industrial use purposes. And what else needs to be done? Looks like they said that potable use of area for the groundwater cannot be used for potable what do we say, or for drinking water, right. That is something that they mentioned. And looks like also fencing around the site and bare areas on treated and capped soil was noted, let us say. As in what I am trying to say here is that we can't just, let us say, be done with remediation and let it be. Obviously, we need to conduct periodic reviews now, right. Why is that? Obviously, to see whether it is performing as you would as you designed it, let us say, or as you estimate it to be. And secondly, let us say there are going to be other aspects, other variables at play. For example, here they looked at damaged site, I mean damaged fencing as in now the people can, people, children, or any other people, let us say, can access this site. That is something you do not want to what do we say happen, let us say, right. And also let us say there are some capped soils, let us say, that seems to be damaged now. So, obviously that is something to keep in mind, right. So, what are the relevant conclusions here? So, highly contaminated the site, let us say, containing a variety of contaminants can be successfully remediated, more importantly at a moderate cost. The key is that moderate cost, and that is one of the reasons why solidification and stabilization is relatively more what do we say widely used. As we saw in that particular graph, this was the most widely used technique, right. And what other aspects? So, again one aspect was that site characterization was an issue. Why is that? If you remember, initially they were trying to look at 2 lakh cubic yards, right, and then after decreasing it as in the threshold risk to 10⁻⁴, and more importantly good or better site characterization to look at the critical areas, they could bring down this volume of contaminated soil from 2 lakh cubic yards to 50,000 cubic yards, right. So, that is remarkably important, careful site characterization. So, again soil action levels, let us say, depending upon your particular objectives, right, and site specific treatability studies, as in obviously let us say a study with respect to the cement fly ash and activated carbon on any soil obviously does not work out. We need to look at different batches from that particular site, right, and that is something that is critically important, and again some innovation in the remedial design and the relevant construction, let us say, right. So, let us move on to another minor case study and we will be done with that though. So, here we are looking at PSA, let us say pepper, steel and alloy, let us say. This is again a Superfund site. Superfund, as we mentioned, is how the relevant US EPA classifies, let us say highly contaminated or sites that are higher up the priority list for remediation, right. So, this is the relevant site out here, look at what we have here, but again here because of lack of time I am going to summarize this, right. So, for battery manufacturing, typically heavy metals, right. So, full scale treatment of 85,000 cubic yards was required. So, 10 acres. The pepper, steel and alloy, these operations were conducted on one, let us say, on one of these 3 tracks. Let us say operations included battery manufacture, heavy metals typically, precast concrete products and fiberglass boards, repair of heavy equipment and service trucks. So, obviously some issues from these 2 what we say modes of usage, but typically this could have led to the contamination, right. And what was it, what is the site here now, how is the site here? So, typically organic loam and peat, sand and limestone here, sand and limestone, keep that in mind because permeability is considerably high here. Obviously, we do not have the relevant thickness and such, but so groundwater is relatively high, about 6 feet below the ground surface. So, that is relatively high groundwater level. So, it was added to the national priority list or US national priority list in 1983, right. And as we mentioned, heavy metals, contaminated with heavy metals and also some PCBs, right. Again PCBs are remarkably toxic, arsenic is carcinogenic and toxic, right. These are the heavy metals as we presumed they would be present because they were used for, or the site was used for manufacturing batteries. So, what is the design here? They looked at, as we mentioned, 85,000 cubic yards. Again the generic case, cement and fly ash. Again there is a particular reason why most people use cement and fly ash. One is the cost and also the ease with which you can work with them, and also it has been seen that for a wide variety of contaminants cement and fly ash and the relevant water forming the CSH matrix is doing the job pretty well now. So, again I am just presenting this particular example to reinforce that particular aspect, right, and mixed with the following and pumped back into the excavation. So, they are backfilling with the same treated soil, right. So, again compressive strength greater than 20.9 psi, but if you remember typically we want or ideally greater than 50 psi. Sometimes people are fine with at least greater than 10 psi, right. So, this falls within or between those 2 ranges. So, hydraulic conductivity as we mentioned earlier 2 less than 10 power minus 6 centimeter per second, and looks like the leachate is below the toxicity criteria now, right. So, let us move on. Again it was listed in 83. Here it ended up the final remedy was selected in 86, relatively faster, but the construction took time, right, almost 7 years and was completed in 93. So, almost here 1 decade or 10 years here, right, that is again something to keep in mind, right. So, maintenance activities, again this is a critical aspect, the 5-year reviews. So, they said looks like trees, right, trees from the site and the cover was damaged. This is an important aspect obviously, though you have this solidified and stabilized mixture, you want to take the extra precaution of let us say trying to see to it that your particular mixture is not exposed to rainfall or any other what we say sources of water or leachate. So, here repairing the cover after removal and inspection of drainage collar for repair. Again throughout the site you are going to have a drainage collar, as in let us say you have rainfall and you have a cap, right. So, what is going to happen to this rainwater? It is going to after runoff it is going to be collected on the sides, let us say. So, thus you need a what do we say drainage collar here, and looks like that is an issue out here, right. So, regulatory status was complete and groundwater quality monitoring is ongoing. Again keep in mind that the review looks at what are the issues that need to be addressed and also is the system behaving as it was supposed to be, right. So, that is something we look at, and I believe I am or I ran out of time today. So we'll be done with this for today's session and move on to what we said the relevant aspects in the next session. Thank you.